Particle physics explored the fundamental particles that make up our universe and the forces that govern their interactions. Generally, each particle has an antiparticle, a counterpart with the same mass but opposite charge. Among these particles, we have neutrinos. They are incredibly small, electrically neutral, and interact weakly with matter. But much about neutrinos remains unknown. For instance, we know they have mass, but we don't know the value of that mass or even how this mass is generated. And perhaps most intriguingly, if particles and antiparticles have opposite charges, but neutrinos are neutral, could they be Majorana-like particles? If yes, then the neutrinos and the antineutrinos would be the same. Neutrinos most commonly appear in nature through a process called beta decay. In beta decay, an unstable nucleus transforms into a more stable one by emitting a beta particle, an electron or positron, and a neutrino or antineutrino. In rare cases, single beta decay is energetically forbidden, so certain isotopes undergo double beta decay, where two beta decays happen simultaneously. This results in the emission of two electrons and two antineutrinos. Now, if neutrinos are their own antiparticles, something interesting could happen in double beta decay. The two neutrinos could annihilate each other, leaving only two electrons in the final state, which will carry all the transferred energy of the system. This process is called neutrinoless double beta decay, and observing it would provide strong evidence that neutrinos are Majorana particles. Not only would this help explain the nature of neutrinos, but will impact other fields of physics such as cosmology. To search for neutrinoless double beta decay, a very rare event not yet observed, we rely on a large detector with a very high radio purity. SNO+, the follow-up of the Sudbury Neutrino Observatory, is one of them. It is located 2 kilometers underground in a mine in Sudbury, Canada, with shields from cosmic rays background, and has a large mass of about 1 kiloton of liquid scintillator. Thanks to the complex cleaning system, SNO+ has achieved high levels of purity, around 10 to the minus 17 grams of uranium per gram of scintillator, minimizing background noise and enhancing sensitivity to neutrinoless double beta decay. In 2025, in order to search for the neutrinoless double beta decay, SNO+ will begin loading tellurium into the liquid scintillator. Tellurium contains tellurium-130, the most abundant isotope known for undergoing double beta decay, with an endpoint energy of about 2.5 MeV. This key value defines the region of interest for neutrinoless double beta decay in tellurium-130. Since there are no neutrinos in the final state, in the case of a positive observation, we expect a peak at this energy. However, before adding the tellurium, it is critical to study potential background events that could hide the neutrinoless double beta decay signal. Using current data from SNO+, I analyze events within a 3.3 meter radius from the scintillator center to minimize the contribution from external noise, such as events coming from the detector components. My analysis focuses on identifying the background events in the neutrinoless double beta decay region of interest and on tuning variables to reject them, ensuring this region is as clean as possible. At the same time, I make sure that the sacrifice of potential neutrinoless double beta decay events is as low as possible. By doing so, I pave the way for detecting a clear, unambiguous signal of neutrinoless double beta decay.